In this presentation, we will be discussing Kirchhoff's current law. First of all, we begin with a quick introduction to Gustav Robert Kirchhoff. He was born on the 12th of March 1824 and he had passed away on the 17th of October 1887 and was a German physicist of his time. He is well known for his impact to the crucial understanding of electrical circuits, spectroscopy, and the emission of blackbody radiation. Kirchhoff's circuit laws, both KVL and KCL, are fundamental to electrical systems that we are studying today. Kirchhoff's current law states that the algebraic sum of the currents entering and leaving a junction, node, or region of a network is zero. This means that the current flowing in is equal to the current flowing out. In the example pictured, we are given a brief understanding of how KCL works in circuits. If we examine carefully, working out the total current at each node, it will help break down the branches and solve any missing current values. In this case, we can clearly see that the sum of the currents, I total, entering into the circuit is equal to the currents exiting the circuit. Here is a slightly more difficult example. It is asking us to determine the values of the other currents, given that IA is equal to 2 amps, IC is equal to negative 3 amps, IG is equal to 6 amps, and IH is equal to 1 amp. Looking at node 1, we can see current IB entering the node and currents IA and IC exiting the node. This allows us to create an equation which will help us solve the missing current values using the current values we are given. In this case, node 1 equals to IB equals IA plus IC, which gives us 2 amps minus 3 amps equals negative 1 amp. This gives us the value for IB. Then we can focus on node 2. Notice how there is two nodes right next to each other. These two nodes can be taken as a single node, as there are no elements between them. This equation gives us IE plus IG is equal to IB plus ID. Doing the math and rearranging where needed, we get the value for ID, which is 5 amps. Continuing this process of nodal analysis, we are able to eliminate and work out each missing current value thanks to Kirchhoff's current law. Following that example brings us to the end of our presentation. Here is a quick summary of what we have learned. Using Kirchhoff's current law, we are able to identify the currents used in the previous example, as it is stated that all current flowing into the circuit, node, or region is equal to the current flowing out. Kirchhoff's current law is fundamental as it is applied in nodal and loop analysis to analyze most series, parallel, or series parallel circuits, and it allows us to find unknown currents. Thank you for listening to my presentation.